Hello, my name is Jacob Magnon, and today we'll be looking at lab number 5, which is going to be over a falling slinky. Let's get straight into it. Alright, so for the purpose of this lab, we're going to predict the motion of a slinky falling to the ground from a stretched position, and we're going to be able to understand the forces acting in the system using the momentum principle. And then looking towards the end of the lab, our results will closely model the position of the slinky as it falls, and we'll do this by creating a computer program using GlowScript. And what we'll actually see in the video is the bottom of the slinky will tell us how to model the forces acting on the entire thing. As far as our formulas and principles, of course we'll need the momentum principle, which can be written as F net equals dp over dt, and we can rewrite that as this right here. And then we'll need to know gravity, which is simply mass times g, which is 9.8. And we'll also be using drag as another force when the slinky is falling. And finally, we have our update formulas for velocity and position here at the bottom. So the first thing we did in this lab was collect data using Tracker Online, and we used this video over here on the left where this man on the right drops this slinky and it falls to the ground. And doesn't show it right here, but this mass right here with the red dot, it stays stationary until this top part has collapsed all the way to meet it. Let's note our system is just a slinky in the earth, and there's nothing in our surroundings acting on the mass. Finally, over here on the right, we see our Y position data, and you see if we set our center of mass as this red dot right here, it does not move up until the slinky is fully collapsed, and then it starts to move towards the ground. Then as far as our initial conditions, we have mass shown here, position, velocity is 0 at the beginning, and gravity and our drag coefficient. So getting into the GlowScript code, over here on the left we see just kind of some conditions that we had just discussed with the mass, some constants, initial conditions, and our t and delta t. And then over here on the right, this is our first loop where we go through the forces acting on the center of mass before the slinky is collapsed. So this is only going to be about half the time. And our forces here are going to be the force of gravity and our tension or spring force, which is really just an equal and opposite force. And when we add these together, there's a net force of 0 acting on the ball or the center of mass. Then for the other part of our GlowScript code, this is going to be when our center of mass is only being acted upon by gravity because the slinky is fully collapsed. And so we'll have gravity and a force of drag, which is shown right here. And then when we add these together, it will not be 0. So the velocity will increase and the position of the center of mass will start to move. And so uh, as I said, we're going to use net force and the update equations to find the velocity of the slinky. And we'll continue this up until the end of the video. And then we're going to print all of these values in the y direction so that we can compare it to the actual experiment. Alright, so here on the left, I created a graph comparing the points created in the predicted model and the points collected from the Tracker Online video. And as you can see, they follow very similar slopes. There's a little bit of difference around here, and some of that error may be from simply tracking issues not being precise enough. Some video errors like the angle of the video or maybe how the slinky was dropped. Maybe it wasn't perfectly straight up and down, and some estimates and calculation. So in conclusion, does this experiment support our understanding of forces? Yes, I think so, because we see that when the slinky is initially released, there are equal and opposite forces of gravity and the spring/tension force acting on the mass, which means there's no force acting on the center of mass that I set, which means it's not going to move, and that is shown in the video. And then finally, when there's nothing pulling up on the mass, then it begins to move because gravity and a small force of drag are the only things acting upon it. But that's about it for this video. Thanks.